Hello and welcome to our little workshop today. It's going to be mostly on mole conversions and stoichiometry. So a little recap, hopefully. What is a mole? So a mole is going to be equal to 1 times 6.022 times 10 to the 23, as you can see right here. It's also known as Avogadro's number, and it doesn't really have a actual unit. It's more like a constant. So this 6.022 times 10 to the 23rd, if you were to write it out, it'd be some really, really big number. So it'd be like 6.022, and then you move that decimal place to the right about 23 times. So you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And you basically just throw in a zero in between all of them, all the way down. And so just like how 1 dozen is equal to 12, 1 mole is equal to 6.022 times 10 to the 23rd. So yeah, they're both basically constants. And so what does that actually mean? So if we were to look at 1 mole of carbon, we can see the symbol for carbon up in the top right-hand corner. You can see it has an atomic number of 6, symbol is C, its IUPAC name is carbon, and it has an atomic mass of 12.011 AMU. But let's say we had 1 mole of carbon. What that basically means is saying that we have 6.022 times 10 to the 23 atoms of carbon. So I guess I could also say if I have 1 dozen of carbon atoms, so if I were to write 1 dozen up here, that'd be like saying I have 12 carbon atoms. Now, similarly, if you had 2 moles of carbon, then you'd essentially just have double the atoms of carbon. And so that would be equal to 2 times 6.022 times 10 to the 23rd. I guess I could also write this as something like 12.044 times 10 to the 23rd carbon atoms. Now, if I were to also have 1 mole of carbon atoms, which is equal to, once again, 6.022 times 10 to the 23 atoms of carbon, it would weigh 12.011 grams. So that 12.011, it actually just comes from the atomic mass that you see up here in the element symbol with the mass and all that stuff. So if I were to weigh that and say I have 2 moles of carbon, then it would actually just be double that weight in grams. So what I can do here is if I were to write the atomic weight of 1 carbon atom, it would be 12.011 AMU. And if I had 1 mole of carbon, so 1 mole of carbon is going to be equal to 12.011 grams of carbon. So this one is going to be for 1 atom. This one's going to be for 1 mole. And so if I had 2 moles of carbon, it would essentially just be double this weight. So I would just multiply all of this by 2. And that would get us just basically double every digit. So that would be 24.022 grams of carbon. And so these relationships, they're actually going to be very, very important when we do our calculations. You're going to be using them over and over throughout pretty much every single calculation that involves moles or atoms or masses. And yeah, so we can also use them as conversion factors. So that's something you should probably keep in mind. So a little example. So let's say we have 1 mole of nitrogen. So similar to our last slide. So 1 mole or 6.022 times 10 to the 23 atoms of nitrogen would weigh exactly or roughly 14.01 grams. So a mole of an atom is going to weigh basically the atomic mass unit of the element, but in grams. So I'm going to try to use these relationships here so that you can try and visualize what exactly or how much a mole actually is. So if I were to have 1 mole of nitrogen, 1 mole of nitrogen would weigh 14 grams. Now, if I had 2 moles of nitrogen, that would just weigh double the amount of 1 mole of nitrogen. So that would be 28.02, which is just double of every single digit. Now, let's say I had 0.5 moles of nitrogen. That would weigh basically half the amount of 1 mole of nitrogen. So what I did in this one to get 7.005 is I basically just divided 14.01 grams by 2. And it makes sense because if you have 1 mole, it's weighed equal to however that number is. But if you have half the amount of that mole, it should only weigh half. So here's a little example that I'm probably going to go through. And then I'm going to have you guys try and practice some on your own. So the first question is, how many grams of nitrogen are going to be in 0.790 moles of nitrogen? So I'm going to start with our given. So our given is going to be 0.790. And then I'm going to write the units, moles of nitrogen. And I want to get the grams. So in order to get the grams, I want to have the grams on the top. And I want to have the bottom to cancel out. So I'm going to put moles of nitrogen as the unit on the bottom. And you can also shorthand moles as just MOL. So what I'm going to do here is I'm going to use this conversion factor that you see right here. So we see that 1 mole is equal to 14.01 grams of nitrogen. So I'm going to put 1 mole on the bottom. And then I'm going to put the mass on the top in grams. So I'm going to put 14.01 grams of nitrogen. And then basically we can just run into the calculator. So these units will cancel out. And then we are left with grams of nitrogen, which makes sense because that's the unit that we'll be looking for in our answer. So if I run this into the calculator, I'm going to get 0.790 times 14.01. And we should get an answer of 11.0679. And remember that we're keeping track of significant figures. So we have 3 sig figs in the given, so 0.790. I'm going to report 3 significant figures. So our answer should be 11.1 grams of nitrogen. And so our next example, we have how many moles are in 58.31 grams of nitrogen. So once again, I'm going to start with our given. So we have 58.31 grams of nitrogen. And we are looking for our units to be in moles. So I'm going to put moles in the top. And then I'm also going to put grams in the bottom, mostly because I want the grams of nitrogen to cancel from the top and the grams of nitrogen on the bottom to cancel out. So we want it to cancel like this. And then it's just a matter of figuring out which number goes where. So once again, I'm going to look back at our example. It's going to be 1 mole is equal to 14.01 grams of nitrogen. So I can put 1 mole on the top equal to 14.01 grams of nitrogen. And if we run that into our calculator, we can just put 58.31 divided by 14.01. And that should get us an answer of roughly 4.162. And so that'll be 4.162 moles of nitrogen. And remember that we can use the conversion factor that we use for the molar mass. You can use multiple values. It makes the most sense for me to use 1 mole. But let's say, for example, I were to do the calculation in another way. So if I start with 58.31 grams of nitrogen, there's nothing wrong with using, for example, 2 moles of nitrogen for the molar mass. But what we have to make sure is that we use the corresponding mass of it. So, for example, 2 moles of nitrogen would weigh 28.02 grams of nitrogen. And it makes sense because if you're to reduce this down to 1, you'd still get 1 over 14.01. And that would end up getting you the same answer that you see right here. All right, so here's some practice. Try these out on your own. You can pause or you can, just look at it and see if you can solve this one. And I'll give you about a minute or two to try the first one, and then I'm gonna give you another minute to try out the second one, and then I'm gonna go over them. All right, so I'm gonna go over the first example now. We have how many atoms are in 4.63 moles of boron? So I'm gonna start with our given. I'm gonna put 4.63. And then what we want in our final answer is going to be our units in atoms. And I guess I should probably include the full units where I include boron. And one conversion factor that we know is that 1 mole is equal to 6.022 times 10 to the 23. So we can use that as our conversion factor. So I'm going to do 1 mole in the denominator. And then in the numerator, it's going to be equal to 6.022 times 10 to the 23. And it's a little bit squished up in there, but yeah. So I'm going to run this into the calculator now. I'm going to put 4.63 times Avogadro's number. And I am getting an answer of 2.788 times 10 to the 24. And so we want to keep track of significant figures once again, and that will round our answer to 2.79. So 2.79 times 10 to the 24 atoms of boron. And just another thing, you might not see it that often, but sometimes you can also represent 1 mole as N with a subscript of A. That is just the variable, or like another way to represent a mole. So this is also equal to 6.022 times 10 to the 23rd. But you won't really see it that often. So the next problem is how many grams are in 9.04 times 10 to the 24 atoms of fluorine. So I'm going to give you another minute or about 45 seconds to see if you can solve this one out on your own. And I'm going to go over it. All right, so how many grams are in 9.04 times 10 to the 24 atoms of fluorine? First, I'm going to start with our given once again. So I'm going to do 9.04 times 10 to the 24. And I'm going to put atoms of fluorine. And so logically, what I remember is that 1 mole is equal to 6.022 times 10 to the 23 atoms. So, and then we also know that a mole of an atom is equal to its atomic mass units, but in grams, basically. So if you can make that connection, this problem becomes a lot easier to solve. So what I'm going to do is I'm going to put atoms of fluorine at the bottom. And now I'm going to put 1 mole in the top. So we know that 1 mole, once again, is equal to Avogadro's number. And then next, we can use that other conversion factor where we know that the mole is equal, a mole of an atom is going to weigh its atomic mass units, but in grams. So I can put 1 mole of fluorine in the denominator. And then I'm going to look at the atomic weight of fluorine up in the top right-hand corner right here. It is going to be equal to 18.998. And if we do all our canceling, then we can do this cancels out here. This one cancels out here. And we are left with our final answer in grams. So if I put this in my calculator, we can see what answer we're going to get. And I am getting 285.18. And that'll be grams of fluorine. Keeping track of significant figures, then we'll just take the first 3. So the final answer should be 285 grams. All right, so continuing on, we're going to be doing more mole conversions, but this time is going to be in molecules and not just atoms. It works basically the same way. So what we can do here is we can actually just treat the mass of carbon tetrachloride and then basically use its weight in AMU, but convert it into grams per 1 mole. So I'm going to give you about 20 to 30 seconds to get started, and then I'm going to go over these problems. All right, so for the first part of this problem, what I like to do immediately is I like to get a weight of carbon tetrachloride. So hopefully you remember the naming rules for molecular compounds. So I'm going to write the formula. It's going to be CCl4. That is going to be carbon tetrachloride. And to get the mass of carbon tetrachloride, all we're going to do is we're going to add up the masses of each individual atom. So in this case, it'll be 12.011 because that makes the carbon. And then 4 chlorines. So I'm going to do 4 times 35.43. And if we work this out, we should get a total mass of, 35.453 is the mass of chlorine. So we should get a mass of about 153.823. So the weight of carbon tetrachloride is going to be 153.823 grams per mole. So now that we have that information, I'm going to use our given. So we're going to start off with 2.13 moles of CCl4. And we want the denominator to cancel out. So I'm going to try and put moles of CCl4 on the bottom. And we know that the conversion factor is this here to the right. So it's 153.82 grams per 1 mole. And then we can check for the units that cancel out. So we can cancel this one out and we can cancel this one out. And if you run this through the calculator, we should get a final answer of 327. .6. And that should round up to 328 grams. All right, the next question, I'm going to give you about 30 seconds. It's going to be asking how many moles are in 112 grams of carbon dioxide. So how many moles are in 112 grams of carbon dioxide? Once again, I like to start off with just immediately breaking down the molecular formula and getting the mass. So carbon dioxide has a molecular formula of CO2. And its molecular mass is going to be 12.011 plus 2 of the oxygens. So each oxygen weighs 15.999. And if we add that together, we should get somewhere around 44. Yeah, so I'm getting an answer or a molecular weight of 44.009. All right, so now that we have this mass, what I'm going to do is I'm going to use our given. So we have 112.0 grams of CO2. And we know that 112 grams of CO2, we want the grams to cancel out. So I'm going to put 44.009 grams on the bottom. is going to be equal to 1 mole of CO2. So I'm going to run this through the calculator, and I'm going to get a final answer of 2.54. moles of CO2. And then if we take into account significant figures, we should get 2.545. And that should be our final answer. All right, so the next or second part of this workshop is basically covering stoichiometry. And so stoichiometry is how we can observe the numerical relationships between our reactants and products when we look at a chemical reaction. And so let's say we're making a pizza and assume that we have to follow the ratios. So the ratios for the recipe of this pizza is 4 cups of flour and 2 cups of tomato sauce and 3 cups of cheese will get you 1 pizza. So what I'm trying to say here is no matter what you do, you have to follow this recipe. If you don't, then you can't make that pizza. So for example, if I were to say, how many cups of flour did you need to make 2 pizzas? Well, basically you can just double all these. So if you were to double that entire supposed reaction or recipe, then we'll get 2 times 4. So that would require 8 cups of flour. That would require 4 cups of tomato sauce. And 6 cups of cheese. And that would get us a total of 2 pizzas because we have double the amount of starting material. So how many cups of flour do we need to make 2 pizzas? We need a total of 8. And so this next part is, let's say we only had 1 cup of tomato sauce and assume that we can still make that pizza. How many pizzas can you make at most? Well, let's see. If I were to put 1 cup of tomato sauce, then we have half the amount of tomato sauce available. So it doesn't really matter how much cups of flour you have. At the very end, you can only make half of a pizza. So this is kind of like an introduction to like limiting reactants. All right, so here's a little example. Let's say we're looking at this following balanced equation. It's 2Fe plus 3 Cl2s yields us 2 FeCl3s. So that basically means 2 moles of iron and 3 moles of chlorine is going to react and it will form 2 moles of iron 3 chloride. And so this question is asking how many moles of iron 3 chloride can be produced if we had 6.88 moles of chlorine. And for this reaction, we can assume that we have plenty of iron. So it doesn't matter how much iron, we just have a ton of it. So I'm going to give you about probably about a minute to see where you're at, and then we can go over them. All right, so we start with 6.88 moles of chlorine. So I'm going to use that as our given. And what we want at the very end is to basically get the moles of iron 3 chloride. So that's going to be our product. So I want the numerator of the conversion factor to be moles of FeCl3. And then we want the denominator to cancel out. So I'm going to put moles of Cl2 in the denominator. And the numbers that we're going to put in here, we're basically just going to look at the balanced reaction and then find out which numbers go where. So if we think about it, remember that 2 moles of iron and 3 moles of chlorine are going to react, and then you'll get 2 moles of iron 3 chloride. So we basically want to find out how many moles of chlorine do you need to make how many moles of iron 3 chloride. So what I'm going to put on the bottom here is 3 moles of iron 3 chloride. 3 moles of chlorine on the bottom, which comes from this part. And then we're going to have 2 moles of iron 3 chloride. So what this conversion factor is really saying, for every 3 moles of chlorine that we have, we're going to generate 2 moles of the product, iron 3 chloride. And so if we do the unit canceling, we can see that moles of chlorine and moles of chlorine will cancel. And then what we're left with is moles of iron 3 chloride. So what we can do here is just put it into the calculator and see what answer we get. And I am getting an answer of 4.586. Moles of iron 3 chloride. And let's see, we have 3 significant figures. So I'm going to put this as 4.59 as our final answer. So if I wanted to, I could actually rewrite this balanced equation in another way. This is going to look very unusual. But basically, I could also write this reaction as 4.59 of Fe plus 6.88 moles of Cl2. And that's going to generate us a total of 4.59 moles of FeCl3. So all it's really doing is following the same ratio that you see in this balanced equation. So you can see that 6.88 is roughly 1.5 times the multiplier of the iron. And you can see the amount of iron and iron 3 chloride, they're going to be the same number of moles, because in the beginning, we start with 2 moles. In the end, we end with 2 moles for the iron and iron 3 chloride. All right, so finally, we have this last set of problems. It's going to be this reaction. So carbon dioxide reacts with water to form C6H12O6 plus O2. So C6H12O6 is going to be the formula for glucose and you can see is written down here. And so for the first part, we're going to balance the equation. So I'm going to give you a moment to try that out on your own and see if you can balance out the equation. All right, so when we balance the equations, what we're trying to do is we're trying to make sure that both sides of the equation have the same number of atoms. So if we compare the left side, which is going to be the reactant, and then the right side, which is going to be the product, and we do a count of how many atoms are on each side, we want these atoms to be the same. And we can do that by either manipulating these coefficients and then seeing if they balance out. So for example, if I were to put like that, this is not a balanced equation, but I'll go into why. So basically, we can see on the product, there's a total of 6 carbons. But on the left side, we see there's only 1 carbon. And so we want to balance out this equation such that this side will have 6 carbons, and we can do that by adding 6 here. But if we do that, we also added a lot more oxygens. So we have a total of 13 oxygens on the left side because there's 12 here, plus 1 from the water. But on the right side, we have a total of 6 plus 2. So the right side has 8 and the left side has 13. So it's still not quite balanced. And basically what we're trying to do is just balance out the entire equation so that they all have the same number of atoms. So I'm going to rewrite the whole reaction. And so I'm just gonna throw in some random number. I like to just try and balance out the easiest part first. So I like to just throw in 6 on carbon dioxide. And if I do that, then both the carbons are balanced. Now I have a total of 13 carbons on the left side and 8 carbons on the right side. So what I can do here is I can look at the other atoms that are present. So I'm going to see there's H2O. There's going to be 2 hydrogens here on the left side. And there's going to be 12 hydrogens on the right side. So another quick way I can balance that one out is I can just put 6 waters, because if I do 6 H2O, then I have a total of 12 hydrogens. So 12 hydrogens on the left side and 12 hydrogens on the right side. So that's balanced. And we also have 6 carbons on the left and 6 carbons on the right. So that part's also balanced. And last, we have oxygens. So the oxygens are still not quite balanced. What I'm going to do here is I'm going to first count off how many oxygens we have. So we have a total of 12 here, 6 here. So we have a total of 18 on the left side. And then on the right side, we have 6 and then 2. So this part is not quite balanced yet. So how can I get O2 to get 12 oxygens on the left side, on the right side? So what I can do is I can just put a 6 right next to the oxygen. And that will get us a total of 12. So we have 12 plus 6 oxygens on the left, 12 plus 6 oxygens on the right. So oxygens are balanced out, carbons are balanced out, and hydrogens are balanced out. So that's going to be our balanced equation. It's going to be 6 CO2 plus 6 H2O generates 1 C6H12O6 and 6 O2. And so the second part of the question is asking if we have 67.6 grams of carbon dioxide and 49.2 grams of water, what is a maximum amount of glucose that you can produce? And keep the units in grams. So this one's quite lengthy. I'm going to give you about a moment to try it out for your own, and I'm going to go over it and just see if you can follow along. All right, so what I'm going to do here is I'm going to actually start with 67.6 grams of carbon dioxide. And the reason why this question is a little bit lengthy is because you're going to find out that one of these reactants, either the carbon dioxide or the water, you're going to run out of them first. And that's going to be basically a limiting reactant problem. So I'm going to start with 67.6 grams of carbon dioxide. And for simplicity, I'm just going to say carbon dioxide, and I'm going to write it up in the top. I'm going to say carbon dioxide has a mass of about 44 grams per mole. I'm also going to say water has a molecular weight of about 18 grams per mole. And glucose is going to have a molecular weight of roughly 180 grams per mole. And O2 is going to have a molecular weight of 32 grams per mole. So I'm just going to use those values for my conversion factors. Those numbers could definitely be a little bit more precise. But what I'm first going to do is I see I have 67.2 grams of CO2. And then I'm going to convert that into moles because we are doing a limiting reactant problem. So I'm going to do 44 grams on the bottom of CO2 per 1 mole of CO2 so that the grams cancels out of grams. Next, I'm going to use the mole ratios or the stoichiometric relationships. So we can see that we want to find out the relationship between moles of carbon dioxide and glucose. So I can put moles of carbon dioxide on the bottom. And then on the top, I want moles of glucose. It's C6H12O6, but I'm just going to write glucose for simplicity. So if you look at the mole ratios, we can see that for every 6 moles of carbon dioxide, as we can see here, it's going to generate us 1 mole of glucose. So I can use that as my conversion factor. So you have 6 moles of CO2 per 1 mole of glucose. And then another conversion factor we can use is that we know that 1 mole of glucose is equal to 180 grams. So I can put mole glucose on the bottom is equal to 180 grams. And I'm going to do some unit canceling. So I'm going to cancel this one here, cancel these. And then our final units is going to be in grams of glucose. So I'm going to put this into my calculator. So if I put all these numbers in my calculator, I'm going to get a final answer of 46.09. So if I put that in 3 sig figs, that'll be a total of 46.1 grams of glucose. Now we had to actually check on the other reactant, water, so that we can determine which one is going to be the limiting reactant, because the limiting reactant is going to judge the maximum amount of product we can actually produce. So I'm going to do basically the same calculation, but instead using water. So I'm going to do 49.2 grams of H2O. And I'm actually going to change the color of my pen so that it doesn't overlap with the red text. So we have 49.2 grams of water. And I'm basically going to follow the same general steps as the portion in red, but just using water values instead. So water has a molecular weight of 18 grams per mole. Once again, I'm going to try and use the stoichiometric relationship between moles of water and moles of glucose produced. So if I look at the reaction, we see that for every 6 moles of water, we can generate 1 mole of glucose. So that's the conversion factor we'll be using. And then let's see, we have moles of glucose on the top. So we want moles of glucose to cancel out on the bottom again. And we know that 1 mole of glucose is going to equal to 180 grams. So we can use that once again as our conversion factor. And so if you put that one into our calculator, let's see what answer we're going to get. And I'm getting an answer of about 82.0 grams of glucose. And so this is going to be the calculation if you use water. These values might change depending on the molecular mass that you used. I used the ones that I put up here on the top. And so we want to find out what's the maximum amount of glucose we can produce. So remember that these mole ratios or these stoichiometric relationships are going to help determine what is going to be our limiting reactant. And so whichever one that we have the fewest moles of is going to be our limiting reactant in this case. So if these ratio of carbon dioxide to waters is going to be 1-to-1, because for every 6 and 6 of each, you're going to generate 1. So if I were to look at the moles here, if you do 67.6 divided by 44, you get roughly maybe like 1.5. But if you were to do the mole ratio or the ratio of or the number of moles of water, given that we have 49.2, we have about, it's a little bit more than 2, because 18 times 2 is about 36. So this is a little bit more than 2. So we have a lot more water than we have carbon dioxide in terms of moles. And because of that, the carbon dioxide is going to be the limiting reactant in this case. And so our final answer is that 46.1 grams of glucose is going to be the maximum amount we can produce. And in most cases, or I'll probably say in general, the reactant that generates the least amount of product is going to be the limiting reactant. So our final answer is going to be 46.1. All right, so that actually more or less concludes our workshop. If you guys have any questions, you can schedule for tutoring. If you haven't already, join us on the virtual STEM Center on Canvas. And you can always email us at this email here and connect with us on social media. We have Instagram and Facebook. And yeah, thanks for coming.